So I'm glad to welcome you all here today for today's really interesting workshop. And I'm very pleased to introduce our speaker today, Dr. Matt Motta. Dr. Motta is an assistant professor of political science at Oklahoma State University, where he teaches courses related to politics, public opinion, research design, and analysis. Prior to working at OSU, Dr. Motta earned his PhD from the University of Minnesota, and then was a postdoctoral fellow here at Penn at the Annenberg Public Policy Center. His current research interests include matters related to public opinion, political psychology, and science and health communication. And Dr. Motta has written for both academic as well as popular media sources, as well as commentated on local news programs. And he's also given many invited talks, including those related to misinformation and controversial science topics, such as climate change and vaccine skepticism. And with that, I'm happy to turn this over to Dr. Matt Motta to teach us all about how to communicate controversial science topics.
Yeah, well, thanks so much for having me. I'm so glad to be here because, as some of you may or may not know, this workshop was supposed to take place in the pre-COVID times, and obviously COVID threw a wrench into that. So I'm glad that we finally get a chance to do this. And of course, it's nice to be virtually back at Penn. As Amanda mentioned, I was a postdoc at APPC, and at the end of our discussion today, we can talk a little bit about some of the opportunities that are available at APPC for science communication research and science communication work. So I'm going to go ahead and share my screen here. And I'm going to give you a presentation, workshop, that's very similar to what Ambika asked me to do last year. So we're going to be able to hopefully accomplish all of the objectives of both this current session as well as your session from last year, which was interrupted by COVID. And that pertains to two different forms of uncertainty in scientific research and how it is that we can overcome it. So before I get into sharing the slides, I just wanted to let you know that I'm going to have the videos muted. So if you have a question while I'm talking, feel free to drop it in the chat or to unmute yourself. But I will note that I'm going to make time at the end of this for questions and discussion. So if you don't mind holding questions to the end, I think that'd be great, because then we can have kind of a more free-flowing conversation. And there is an activity embedded in this as well. So we will have a couple of chances to talk. But yeah, so if there's nothing else, I'm going to mute your videos and get right to it. So today we're going to talk a little bit about communicating uncertainty in scientific research. And when we think about uncertainty from a science communication perspective, I think we can really classify uncertainty into two different types. And that's how I'm going to structure this workshop today. In the first hour, and it won't be the full hour, I'll try to be brief with my remarks. But in the first hour, I'm going to talk a little bit about what it means to communicate the results of scientific research effectively to what I like to call uncertain audiences. And I'll unpack what that means in a little bit. Then we will have a brief break and a workshop activity, and we'll talk a little bit about it. And then we'll come back for the second hour and talk about communicating uncertainty in scientific research itself, in the process of doing science. How can we effectively communicate what it is that you and I deal with on a daily basis? So that's how I'm going to structure this workshop. And as I mentioned, for the first hour, we're going to talk a little bit about uncertain audiences. Here's what I mean when we call an audience of scientific research uncertain. People in our audiences, the people with whom we are trying to effectively communicate about scientific reality, scientific facts, scientific studies, the people in our audience engage with communication about scientific research in different ways. People bring different things to the table, politically, socially, psychologically, when they encounter us or someone else talking about the work that we do. And certain people in our audiences, as we're going to talk much more about for the remainder of this lecture, might be motivated by some factor or set of factors: policy, politics, religion, cultural worldviews. They might be motivated for reasons that have nothing to do with the science necessarily to reject what it is the science finds. And here's the big trouble for us. Here's the problem for us as science communicators. We don't always know who these individuals will be and how their motives might shape resistance to the science that we hope to effectively communicate. In that sense, our audiences are to some degree uncertain. We know that we might encounter some amount of resistance, but we don't know how much. We don't necessarily know among whom, and we don't necessarily know why. So how is it that we can effectively communicate the results of our work to audiences where we don't know what some of these stumbling blocks might be? And you might see on the right-hand side of the screen here some examples of what those stumbling blocks might be. The tight link, for example, between partisan politics and the acceptance of anthropogenic climate change, something that's shared by many conservatives, right-leaning folks in the US public, as well as among elected officials. So how can we effectively communicate scientific research that audiences might be motivated to reject? That's really the central question that we want to answer. And our research, my colleagues and I, suggests a potential solution. And that's what I'm going to refer to throughout this talk as the diagnosis and treatment model, using some of the language of medicine in order to do this, and some kind of corny clip art on the right-hand side of the screen. But as the name implies, there's really two main things that we need to do in order to be able to effectively communicate science to these uncertain audiences. And they might seem fairly straightforward, but they're actually really difficult to do. The first is to diagnose the problem, to identify the social, psychological, political, and other factors that might lead some people in the audience to whom we want to communicate the results of our research, whether that's the American public, whether it's university students, whether it's our extended family at the Thanksgiving dinner table. Identify what factors might lead some people to be motivated to reject scientific consensus in a particular area. And what this requires us to do is to perform scholarly research, often public opinion research, but there's other types of research that we can do as well, that not only tells us how pervasive scientific skepticism is, but assesses what some of its correlates are. Why are some people more skeptical than others? That's how we figure out what the problem is. That's how we make less uncertain our uncertain audiences. And then once we've done that, we can design treatments informed by our diagnoses, so to speak. Our communication, and this is really the core finding that I'm going to present today and that my colleagues and I think tends to be effective. Our communication efforts to reach those people should be informed by the causes of science skepticism. What we're going to find today is that ignorance of scientific reality, not knowing the facts, often isn't the problem. And so hitting people over the head with the facts, telling people you're wrong and here's why, that's often not the most effective solution, because that's not usually the problem that we diagnose in stage one. What we tend to find to be effective is to say, okay, why is it that some people in my audience are motivated to reject science? And to then ask, how can we use that motivation to then structure communication efforts that aim to get people on the side of science? I'll show you examples of what that looks like shortly, but this is the treatment stage where we say, based on what we know about the problem, let's use that to inform our solution. And it might not work the first time or the second time, or as my colleagues and I are finding with some of our COVID-19 vaccine messaging, the 10th or 11th time. But that's part of the process. Part of the process is figuring out what people believe and then trying to do something about it and going back to the drawing board when it doesn't work. So let's unpack the first part of this procedure a little bit. How do we diagnose a problem? How do we figure out why some people in our audiences might be motivated to reject science? And what we know from research in social psychology, from Ziva Kunda and others, is that really all human reasoning can be thought about as taking on one of two forms. Sometimes we want to make accurate judgments. We want to know the truth about some stimulus in our environment. This is the type of thing that's very useful to us as humans in an evolutionary perspective. If, say, we wanted to avoid a threat, if we wanted to get away from a bear lurking in the wilderness or something like that. There's another type of reasoning which is known as directionally motivated reasoning. Accuracy motivated reasoning is one type. Directionally motivated reasoning is the other. And what that implies is that sometimes we want to see the world in a particular way. When there's a bear in the woods, it behooves us to know if that's potentially a threat to us. We might be more motivated by accuracy. But there are times when we want to see the world in a certain way. I'm a huge sports fan. I grew up outside Boston. I root for teams that recently haven't been doing all that great. I would like to believe that they're doing better than they are. And I can make complicated arguments as to why I think that might be the case, but that doesn't necessarily mean that it's true. And so there's a great paper from Kraft, Lodge, and Tabor published in 2015 in the Annals of Political Science that offers some insight into how it is that humans apply this directionally motivated reasoning to science, to matters of scientific consensus. And some of their work is on the right-hand side of the screen, but you don't even really need to internalize that or read it all too closely, because there's one really simple take-home point from this research. It takes effort. It's not easy. To see the world in a particular way, to arrive at conclusions at which you want to arrive in the face of scientific facts, in the face of being presented with scientific research papers and testimony from folks like Dr. Fauci, it takes a lot of effort to see the world, to convince yourself that what you want to believe to be true is in fact true. Our goal as science communicators can be stated in the language of social psychology as making an effort to convert directionally motivated reasoning with respect to science into accuracy motivated reasoning. And one of the central principles, which I'll again hit on here, is this idea that directionally motivated reasoning is effortful. Because so often we make the assumption that motivated reasoners are stupid. People who reject vaccine science are stupid. People who think the earth is flat are stupid. They don't know the facts. What this implies is that if only people knew the facts, they would come around to the science. And what we're going to see today is that is often not the case. Why? Because motivated reasoning is effortful. We need to, as I suggest on the previous slide, but again, you don't necessarily need to internalize this figure on the right-hand side of the screen, we need to generate counter arguments. We need to be able to say, here's what the facts are, and here's how I am going to weaponize those facts in order to believe what it is I want to believe, coming from the perspective of a motivated reasoner. Counter-arguing is a heck of a lot more effortful cognitively than simply accepting something as true. It takes work. And what follows from that is this idea that motivated reasoners are not stupid. They're not people who necessarily lack information about science. In fact, very often, they're people who have lots of information about the science because they have become so accustomed to generating counter arguments, to seeing the world and substantiating this view of the world that is the way that they want to see it. They use accurate information in service of, ironically, rejecting it. So people who believe conspiracy theories, people who accept misinformation, people who think that vaccines aren't safe and that the world is flat, they are often using information in service of arriving at a misinformed view that is consistent with something else that they want to be true about the world, whether that's a political orientation or a religious orientation or something like that. And let's take the example of flat Earth theory here. Let's assume there's some audience, some group of people that are motivated by, let's say, a particular religion to want to see the world in a very two-dimensional way, a literally two-dimensional way, right? That it is flat and not a globe. Perhaps this helps substantiate some elements of religious doctrine. I think we can all kind of figure out what some examples of this might be. So here's a screen grab that I took from a prominent flat Earth theory website. And before I tell you what's on the screen here, let me just say I teach a class on misinformation at Oklahoma State. And one of the things that I tell my students on day one is if you want to know something about the curvature of the Earth, ask a flat earther. I've done it. It's impressive how much knowledge folks who want to believe that the Earth is flat have about physics, about astronomy, because they are using that information as a jumping off point to then try to generate counter arguments that enable them to see the world the way they want to see it. So look at some of the rebuttals, again, counter arguments, things that are effortful, that this Flat Earth website has put up on the internet as a way to talk to people who are convinced that the Earth is round and a globe. How is there a magnetic field? Magnets can't be unipolar. The author of this writes that while it's true that unipolar magnets can exist, this isn't a problem for flat Earth. This is because ring magnets, which are shaped like, you guessed it, a flat disk, are capable of having radial magnetization. Does that sound like somebody who's uninformed to you? Does that sound like somebody who doesn't know some basics of science and the scientific method? They're not. These are people who are making very sophisticated counter arguments in service of seeing the world the way that they want to believe it. So what you can kind of take away from this image is the use of the language of science, albeit incorrectly, by people who clearly understand the science well and are perhaps motivated to reject it. And it's studying that motivation that, how do we get from looking at what flat earthers say on the internet to then saying, well, how do we know that people are actually motivated to see the world in a particular way because of politics or cultural worldviews or religion? It's there that my colleagues and I, and some of my advisors and people I've worked with in the past, that's where we come in, studying the applications of directionally motivated reasoning. So in a really classic, I think, study from Dan Kahan, who, in the interest of full disclosure, was my advisor at Yale Law School when I was a postdoc. But Dan has done some really interesting work on what the science of science communication is. And one of the things that Dan did in a 2015 study that was published in the Journal of Science Communication is he attributed two different statements to, in the context of an experiment, or what we in social science refer to as a survey experiment, he attributed two different statements to a hypothetical scientist. The scientist's credentials didn't change across experimental treatment groups. But what changed was whether or not that scientist was talking about climate change as being a high risk or a low risk activity. And what you see is that when climate change is described as a low risk activity in green, folks who identify as more politically conservative, we know, I don't think I need to explain to anyone on this call, but let me know later if you want to talk a little bit about how we got to this point. But there is a very strong partisan divide with respect to who thinks that anthropogenic climate change is both real and a problem. What we see here in this figure is that people who self-identify as being very conservative, strong Republicans, tend to view more favorably, that's on the y-axis, the scientist when his comments are perceived as low risk or are low risk comments. And conversely, that strong conservatives are not likely to trust that person or to view the scientists favorably when making an argument that runs contrary to their political opinions. And you see the exact same thing going on the left, right? That folks who are very liberal on the left-hand side of the screen are viewing the scientist as less credible when he says that climate change is low risk, and more credible when he says that it's high risk. And of course, one of these views is correct and one of these views is incorrect. That is not lost on researchers. But the point here is that when science becomes politically contentious, for whatever reason, well, views about science and the scientists, the people who produce it, are politically contentious as well. We held constant, not we, Dan, held constant this person's credentials, where they came from, their name. All that changed was his recommendation about the science. And when that science cut against what people wanted to believe, what people believed was consistent with their political ideological worldview, all of a sudden, the nature of science itself changes for these people. And knowledge plays a big role in this. What people know about science, their knowledge of scientific facts, helps facilitate directionally motivated reasoning. And I'm going to again draw on some of Dan's research with some of his colleagues to make this point. And this is a somewhat complicated figure, but I'll describe what it is that you're seeing here. Essentially, Dan and his co-authors did a study where they asked people to solve a simple math problem. It's what's known as a covariance detection task. The specifics aren't super important for our purposes here, but here's what's important. In one version of the math problem, Dan was comparing whether or not a skin cream was effective at increasing or decreasing the prevalence of a rash. That was randomly assigned to one half of a public opinion survey. This is another survey experiment. And the other half were given a question, exact same question, same covariance detection task, same numbers input into this math problem, but instead they were given information about whether or not a policy, a political policy, a public policy, increased or decreased crime, which, again, I probably don't need to explain to most folks on this call, but crime is a pretty politically contentious issue here in the US. And what he finds, now this is looking at the x-axis. The x-axis here is telling us who's more numerate. Numeracy is a measure of quantitative reasoning. So the further right you go, the more numerate people are. The further left you go, the less numerate people are. You see in the top half of the figure, when we're talking about rashes and skin creams, exactly what you'd expect to find. It doesn't matter if you're a Democrat or Republican. If you're better at doing math problems, if you're more numerate, you're going to get the answer right. But look at what happens in the bottom half of the figure when we start talking about crime. All of a sudden, and again, I'm not going to walk through the specifics of this experiment, but all you need to know is that there were some conditions in which Democrats came out ahead, others in which Republicans come out ahead. And what you see is that more numerate people were actually more likely to get the wrong answer in some of those problems if those problems disagreed with their ideological priors. If the result of doing the question correctly implied that their preferred outcome of the policy based on their partisan reputation was incorrect. They were more likely to get the question wrong than some people who were less numerate. And so what this implies is that people who are plenty knowledgeable and plenty capable of solving complex problems can weaponize facts in service of seeing the world the way they want to see it. And perhaps even a more tractable example of this, Dan, in the same paper I referenced before, the 2015 What is the Science of Science Communication paper, looked at people's what he calls ordinary science intelligence, which is essentially a measure of how much people know about basic scientific facts, as well as their familiarity with the scientific method. And then asked people a series of questions about the basic science facts. So for example, the idea that electrons are smaller than atoms. Now, what you see, the blue lines on these figures, the y-axis, I should say, is the probability of getting a response correct. The x-axis is how highly you score on this ordinary science intelligence measure. Blue lines, people below average with respect to religiosity, how frequently they attend religious services. And orange is above average. And what you find is that for questions that really don't have any clear linkage to religion, you know, electrons being smaller than atoms, the composition of the Earth's atmosphere, a probability question, right? For all of those, it doesn't matter if you're above or below average in religiosity, if you understand the scientific method better, you're more likely to get it right. But look at this last pane. Human beings, as we know them today, developed from earlier species of animals. Well, that's very contentious to some folks who might be highly religious, right? The idea that evolution shouldn't be taught in public schools is something that still galvanizes support among more religious people from certain religious faiths to this day. And it's something that has been part of American history for a long, long time. And what you see, perhaps somewhat predictably, is that people who are below average in religiosity exhibit the same pattern that we saw in every other panel. If you're more familiar with the basics of science, you're more likely to think that humans evolved from animals. But if you're above average in religiosity, it doesn't matter how much you know about science. You're rejecting it. In fact, the people who know the most about science are actually a little bit more likely to reject that evolution is real and happening. And so what, again, we see evidence of here is not just this idea that facts won't necessarily save us from misinformation, but that people who are sufficiently motivated to see the world in a particular way can use scientific facts in service of seeing the world the way they want to see it. So what does this mean for us as science communicators? How can we communicate science to uncertain audiences? Here's what doesn't work. Or here's what I should say doesn't always work, because there are situations in which it can work, and I'm happy to talk about what some of those are. But generally speaking, if people are not necessarily uninformed about science, and if on the other hand, people are using science to reject it, well, then it stands to reason that speaking to the public the way scientists speak to one another, talking about facts and scientific debates, telling people you're wrong and here's why, that's probably not going to work. Because, as I mentioned earlier in this talk, information and the lack of it isn't the problem. In fact, information could be facilitating this problem. And we see this all the time in scientific studies. Again, it's not universally true, and we can talk about exceptions later on. But in a really interesting study from Brendan Nyhan and Jason Reifler on flu vaccine uptake, and again, I'm not going to explain the entire study, but here's the basic gist of it. They gave people different types of information, corrective information, about the idea, this piece of misinformation, that the flu vaccine can give you the flu. And you know what they find is that for people who believe this to be true, that giving people, and I'm pointing to this with a red arrow on the screen, people who believed this piece of misinformation about the safety of the flu vaccine, if you gave them the facts and said, well, actually, here's how vaccines work. Here's why you're not particularly likely to get the flu. from, in fact, it's impossible for you to get the flu from this vaccine, they were less likely to want to then get a flu shot. What we see going on in this study and in other studies that Brennan and Jason have done is that it's possible sometimes to give people corrections, to say, you're wrong and here's why, and maybe get them to then say, yeah, okay, I was misinformed about X, Y, and Z. But often we see not just a backfiring effect where people will double down on the misinformation they once held and generate counter arguments as to why they think it's true. But they will do what psychologists refer to as, or exhibit what psychologists refer to as a continued influence effect, whereby even if you can move people's attitudes and get them to admit that they were wrong about something, you might not necessarily change their behavior. And that's what Brendan and Jason found in this study, was that they were able, and in a series of other studies, that they were able to convince people, yeah, I might have been wrong about this, but I'm still not getting my flu shot this year. So even if we're able to correct misinformation, well, let me just take a step back and say, one of the things I often say to my students in my course on misinformation is that misinformation about science itself wouldn't necessarily be problematic if people didn't take action on it. It would maybe normatively be a bad thing. I think arguably it would be a bad thing normatively if people were misinformed. But if nobody was acting on it, well, then we might not care about it as much, right? But in a situation like this, where even our efforts to communicate the facts might be able to move people's attitudes, but they don't necessarily move people's behaviors, whether or not they get vaccinated, well, then that's a problem. Because in this application, what we're trying to do is encourage vaccine uptake. So what can we do? One of the things that my colleagues and I find to be very effective, based again on this diagnosis and treatment model, is to try to make an effort to engage people on their own terms, while making an effort to, at the same time, and this is really difficult, stay true to the science. I am aware that what I'm about to say is not something that's necessarily easy to do, and it's not necessarily something that's foolproof. But this is the type of work that needs to be done, in my view, in order to be able to effectively communicate science. So in a paper that my colleagues, Robert Ralston and Jen Spindle and I published this past year, we took a look at this idea, which I've mentioned already in this talk, that ideological conservatives in the US are more likely to think that climate change is not caused by humans and that it's not much of a problem. And so we started thinking, okay, how can we convince conservatives to agree that climate change is caused by humans and that it's problematic? And one of the things that we turn to in the science communication literature are the sources of messages. Some people are more credible communicators than others. And for people who are motivated to see the world in a particular way, particularly with respect to a particular political leaning, well, folks who come from that side of the partisan aisle, studies have shown, including ours, tend to be the most effective communicators. Somebody who shares your views in some other area is more likely to convince you to do something or to believe something than someone who doesn't necessarily share those values. Seems pretty straightforward. It's actually a pretty hard thing to do. And one of the things that we did, now this study was conducted in the middle years of the Trump administration. One of the things that we looked at was the idea that there were plenty of folks within the Trump administration, including Defense Secretary Jim Mattis, who believed that climate change posed a pretty hefty national security risk. And we thought that that could make a really useful source for communicating climate reality, in part because we know, based on previous public opinion research, that one of the most trusted groups, not just on the ideological right, but in America more generally, are military service members, the troops. Who better to convince conservatives of climate reality if you can't get prominent Republicans like, say, the former president to do it, who better to do it than groups with ideologically conservative reputations that folks on the right tend to really, really have a lot of respect for? And so what we found in this study is that and this is what's exemplified in the gray line that you see here. There's a blue line and a gray line. The y-axis is the probability in this first panel that people believe that climate change is human cause. The x-axis is ideology, with people on the right being the most conservative. And what you see is that this black line, sorry, got my colors mixed up. Black line is our control group. They see no information. But the blue line, these are people who are getting a message that says, hey, climate change is a national security concern, and it's something that many folks in the military, the troops, are concerned about. What you find is that the probability on the right-hand side of the x-axis that people think that climate change is human cause is significantly higher when we tell people this is something the troops are concerned about than it would otherwise be were we to do nothing. And you see similar effects with respect to concern, although the statistical significance of those effects is a little bit more tenuous. But the general idea here is that by making an effort to understand where people were coming from and saying, look, we could give you the science, right? We could try to convince you that you're wrong to believe what you believe. Or we could change the argument up a little bit. We could focus on something else. It doesn't necessarily reify the science, but it is at least conveying the main talking points from the science from a communicator that this group tends to trust. We were able to move acceptance of climate change, which is a really hard issue to get people to move their opinions about, in part because it is so partisan and controversial. And just because we're all living through a global pandemic right now, I thought I'd talk a little bit about vaccines. My colleagues, Chrissy Luns-Trujillo, Tim Callahan, and Stephen Sylvester, and I published a paper this past year where we took a look, and this was conducted before the pandemic, at parents' willingness to vaccinate their children. And what we know on the basis of previous public opinion research that we published in social science and medicine is that people who strongly value what we psychologically refer to as moral purity, which is panel B on this screen, the tendency to view one's body as a temple, to not want to put foreign substances in it. Well, it makes a lot of sense that people who see the world this way are going to be more likely to think that vaccines are unsafe, are going to be the types of people who don't want to vaccinate their children. And so what we did was we basically tried to turn that logic on its head. We made an appeal to people who believe those things. And we said, look, we get it. Vaccines are necessarily invasive. They entail putting a foreign substance into your body. But you know what else is invasive? You know what else is a foreign substance that can potentially do harm to your body? Measles, mumps, and rubella, the very diseases that this vaccine is designed to protect you against. And when we give people that information, when we deflect a little bit and try to recognize the fact that people who strongly value more moral purity might be averse to vaccination, what we find, this is the blue line on the screen versus the control group, which is the green line on the screen, that the probability that people think that vaccines cause autism increases only slightly as levels of moral purity increase in this group that we made a targeted appeal to try to say, look, we get where you're coming from. In the control group, right, you see the predicted and I think quite reasonable effect that people who are scoring highest in moral purity are the most likely to be misinformed. We're able to neutralize that quite a bit by simply trying to make an effort to understand where people are coming from and use that to inform our communication strategy. And I've got a couple of other thoughts here, but in the interest of time, we can talk about those thoughts in Q&A. I'm going to turn things over scheduled activity. And if I can come back to some of those thoughts later on, I will. So I'd like us to do, and the way this is going to work, and I understand that you've done something similar to this before, is that you'll all be sent into breakout rooms for 10, 15 minutes or so, and then we'll meet back and we'll have a discussion, all of us. But what I'd like you to do is to identify and navigate motivated resistance to science and scientific research, and use that to inform a communications strategy by which we can try to get people on the side of the science. So imagine the following scenario, and this is one that is essentially quite real for many of us in the audience here, right? Some of you are going on the job market, or you're on the academic job market right now. This is something you might face on a daily basis. So imagine that you've just been given a job at a large Christian university somewhere in the US South, and you've been asked to deliver a lecture on recent advances in the study of evolution. And you know, again, this is the diagnosis stage of the model, right? You know, let's say based on public opinion research or anecdotal experiences, that the majority of the student population at this university identifies as conservative, politically conservative. And that many of them are highly religious. They attend religious services on a weekly basis. Using the insights that we've talked about in the lecture up to this point, what I'd like everyone to do is to discuss potential forms of resistance you might face when presenting this research. So how might politics and religion shape opposition to the research that you're about to present? And then what's most important is thinking about how you can strategically tailor your presentation of the facts to effectively communicate this research in light of those challenges. So I'm going to pop the videos back open here and ask if anybody has any questions before we adjourn to the breakout rooms. And that's questions about the assignment. I'll take more general questions in a moment. Okay, I see the chat is, I got some questions in the chat. Let me pull it up. Okay. Oh, but they're, oh, general question. Yeah, Michael, we'll talk about, and I haven't read all of these yet, but we'll talk about that at the end. I'm gonna save time to talk about that at the end. Thank you, though. Okay, so either Alice or Amanda, if you want to send people to breakout rooms, I think 10 minutes is probably sufficient, and then we can have a general discussion and then move into the rest of the lecture.